Alright, so this one we got a person up at A on a slide, and he slides down to B. We're given the height of the slide. The person starts from rest at A, and they want to know the speed at B, and the normal force on the boy at B. But let's find the speed at B first. If we wanted equations of motion to do that, that wasn't such an easy problem. Let me show you something. Well, there's a couple ways to handle it. We can say the kinetic energy at A plus the work, or the summation of the work done from A to B, is equal to kinetic energy at B. It started from rest. What kind of work did it do? Well, it took this weight of 40 times 9.81 down a distance of 7.5 meters. Alright, now that equals the new kinetic energy, 1/2 mv final squared. And we can solve for that right away. V final ends up being 12.1 meters per second. Now, if that's not as intuitive, using work energy principles, I'm going to teach you kinetic energy plus potential energy is equal to kinetic plus potential in the final state. And you've done this before, you've just seen it as kinetic energy plus potential energy is equal to kinetic plus potential, where potential could be things like 1/2 kx squared for a spring. It's storing energy. It could be mass times gravity times height, gravitational potential. We could have chemical potential too, and I'm going to go over all that. But if this method right here doesn't quite make as much sense, we can still do 1/2 mv squared. You've done this before in high school, I know you have. So our kinetic is always 1/2 mv squared. Our potential would be some mgh at 1, or A in this case. And it would end up being some new 1/2 mv squared at B plus some mgh at B, where if we set this to 0, then this term goes away because its final comes down to a final position of 0, and it started from rest, so that term goes away. Then we get to cancel the masses because they're the same thing, and what we get is the velocity is equal to the square root of 2gh, and we get the same exact thing, 12.1 meters per second. And I'm really going to stress that if possible, we're going to use this conservation of energy method right here. We got to go through all the steps of work and energy in general before we get to the conservation of energy. Just know we're heading in that direction. We'll use this as little as possible. Still, super important. Two of the best or most important principles in this class, in my opinion, for dynamics. In the future, you'll learn about something called the Lagrangian. It's another energy method. Just involves derivatives and partials. So, now that we have that velocity, first of all, that was one of the things they were looking for. They want to know what the normal force is. Well, at the bottom of that curve, it goes flat. So right here, that's not straight. Right here, it is flat. And what we would have, if this is our mass, or the boy, is mg pointed down and some normal force pointed up. Alright, now if we sum the forces, we get mass times the acceleration in the normal direction. And we get a normal force pointed up, mg pointed down. And remember, we can substitute v squared over rho. The only thing we don't know, because we can substitute v right here, is rho, but remember, rho can be found by taking this path they gave us, 0.075x squared. Taking two derivatives, and they want to evaluate the whole thing at x is equal to 0. So after taking the derivatives, you get 1 plus 0.15x, and that whole thing gets squared, and then that whole thing gets raised to 3/2, and then the second derivative goes on the bottom, the absolute value, and that's evaluated at x is equal to 0. And when you do that, you get a radius of 6.66666666 meters. So substituting that into there, we can find the normal force because we know the mass, we know the velocity, and now we know the radius of curvature. We get a normal force equal to what is it? 1,275.3 newtons. There you go.